It is August 1958 at a Texas Instruments manufacturing plant. The entire facility is completely empty. Management has shut the doors so the workforce can take a mass summer vacation. But Jack Kilby is sitting in his lab. He was hired in May, which means he hasn't accrued any vacation time yet. Left entirely alone, he starts running the numbers on the company's cost structure. Because the building was deserted, Kilby had no supervisors around to assign him tasks, and no senior engineers present to tell him how things were supposed to be done. At the time, building electronic equipment required a massive amount of manual labor. Technicians would sit at a workbench and physically hand-solder dozens of highly specialized components together with small wires. For complex systems, especially in the military, the scale of this physical assembly process became staggering. A single B-29 bomber required nearly 1,000 fragile glass vacuum tubes, alongside tens of thousands of other distinct passive devices, all individually wired. The industry called this the tyranny of numbers. Every time an engineer added a wire to connect two parts, they introduced a new place where a connection could snap, vibrate loose, or overheat. If you look at how this scales on a chart, the physical problem point becomes obvious. As a system's complexity rises linearly, the number of potential failure points curves violently upward. You quickly hit an unsustainable spike. Engineers wanted to build advanced computers and sophisticated missile guidance systems, but they physically couldn't add any more wires without the machines collapsing under their own complexity. Back in that empty Texas Instruments lab, Kilby was meticulously detailing the costs of his company's manufacturing process. The numbers were extremely high. He deduced that a semiconductor manufacturer could only become truly cost-effective if they stopped buying outside parts and made every single component out of the semiconductor material itself. Up until that summer, the standard practice was to mix materials. You built resistors out of carbon, capacitors out of mylar films, and strung them together with metal wire. Kilby realized that none of those separate materials were actually required. You could sculpt the resistors and the capacitors directly into the same block of silicon or germanium that housed the active transistors. He began sketching out his theory. His engineering notebook shows a phase shift oscillator relying entirely on internal p-n junctions to act as capacitors. To replace external resistors, he used the natural resistance inherent in the germanium crystal, a property he called bulk resistance. These sketches quickly evolved into a blueprint for a complete, working flip-flop circuit laid out across a single, solid crystal wafer. On September 12, 1958, he put his theory to the test. He connected power to a tiny, crudely cut sliver of germanium. It immediately oscillated at 1.3 megacycles. The integrated circuit worked. By carving the entire system out of a single block of material, Kilby removed the need for separate parts entirely. With no separate parts, there were no wires to snap. He had completely bypassed the tyranny of numbers. Once circuits were consolidated into monolithic pieces of crystal, manufacturing stopped being a mechanical assembly job. It became a chemical printing process. Another researcher named Gordon Moore recognized that with enough investment, this chemical printing method could be made almost arbitrarily better. You could keep shrinking the components down, printing more and more of them onto the exact same surface area. This graph illustrates the immediate, violent shift in technological capability. The slow, steady growth of the vacuum tube era suddenly pivots into a near-vertical explosion of computing power once the integrated circuit takes over. And looking at this experience curve chart, you can track the resulting economic freefall. The cost of a single circuit function plummeted from $10 down to a fraction of a penny. That massive drop in price is what allowed computing to leave corporate labs and bomber aircraft, eventually finding its way into our homes, our pockets, and the foundation of modern society. We live in an incredibly fast, loud digital economy today, but its architecture traces back to the absolute stillness of an empty room. Jack Kilby solved the era's greatest engineering bottleneck because everyone else went on vacation, and he stayed behind to think.